Well, we said that the logarithmic function was the inverse of the exponential function. So let's look at the exponential function in a little bit of detail. And let's draw up our basic exponential. And there it is, our familiar curve. They all pass through 1 on the y-axis because, of course, our little line, anything to the power of 0 is 1. That's if the base is bigger than 1. If the base is in between 0 and 1, then it would go the other way because you're basically saying a fraction to the power of x. So, for example, a half, but a half is 2 to the power of negative 1, so it's the same as doing a to the power of negative x, so it would reflect over. So it also means that the red one could be a to the negative x when the base is in between 0 and 1, and the blue one could be a to the negative x when the base is greater than 1. The domain, all real x, range y is greater than 0. So y equals e to the power of x is the natural base, e. And so e is basically just another irrational number. Its formal definition is there. The limit as n approaches infinity of 1 plus 1 on n to the power of n. So as n gets bigger and bigger and bigger, you'll get closer and closer to this irrational number e. And it's an amazing number. It appears everywhere for some reason. That's just the beautiful thing about maths. And it appears in science, it appears in nature, it appears everywhere. These calculations, and all of a sudden this number e just comes out. It appears in probability. Approximately, it looks like it recurs. And that's just because of the limit of your calculator screen. And so you see 2.718281828, but trust me, after that it goes off to other numbers, because irrational numbers, as we know, we can't write as a recurring decimal, but pi being the classic one, of course. And so if you went to your calculator, because you have got a lovely E button, that's the inverse of what you think is the in button, ln, but you can do e to the power of whatever. So if you had to find e cubed, well, that's easy enough. Use that key to the power of 3. And 3 decimal places, we get 20.086. All right, let's have a look at the interesting bit. How do we differentiate exponentials? Because if y equals e to the power of function x, the derivative, and this is where you've got to be really careful because it's not a polynomial, because e, remember, is a constant number. A polynomial is when the base is x, is an unknown. Now with a polynomial, we would subtract 1 from the power. But here the power stays the same, right? Because the function is actually in the power. So you differentiate the function, that goes out the front, and then e and the power stays the same. What happens if the base is not e? Similar with the logs, we can do a change of base. I could turn this into a log, because it would become function x equals log base ay. I could, instead of finding into y the x, I could find the x to y and then go backwards again. But that's a lot of work. Basically, it just turns out you end up multiplying by the natural log of the base. And that's all to do with the change of base rule. When we differentiate logs to non-natural base, we divide by log a. When it's exponentials, we multiply by log a. Okay, back to what I was talking about before. So when you have just e to the power of x, easiest question there is, what's the derivative of x? 1. So 1 goes to the front and it's e to the x. World's easiest question. But what that basically means is, if you think about it, is with that exponential curve, the slope of the tangent at any particular point is equivalent to the y value. And that explains why it gets steeper and steeper and steeper. Because as the curve's going, the y values are getting bigger and bigger and bigger, so the curve gets steeper and steeper and steeper. So if it was e to the 5x, we differentiate the 5x, and we get 5e to the 5x. E to the 4x plus 3, very tricky that one. Ooh, 4x plus 3. 4e to the 4x plus 3. Doesn't have to be, of course, a linear function. X squared plus 3x plus 2, and we get 2x plus 3, e to the power of x squared plus 3x plus 2. Make sure you use parentheses there, so it's all of it times the e to the power. Product rule. Okay. So you do actually have 2 distinct functions there, because the 3x squared is times the e to the 4x. write down the first, diff the second, plus write down the second, diff the first. 12x squared e to the 4x plus 6x e to the 4x. And again, I guess it depends what you're going to go and do with the derivative as to whether you factorise. Most of the time we use these sorts of things to solve equals 0 for stationary points, so we probably would factorise. So in this case, this particular curve, whatever it happened to look like, it would have two stationary points. There's 2x plus 1 could equal 0, and the x could equal 0, but of course the e to the 4x can never equal 0. That won't produce a stationary point. Anarchy! Bring down the power. So 7 comes out to the front, lower that power 6, put the boot in, 3e to the 3x, tidy that one up. There we go, 21e to the 3x. So all the rules are the same, just another function to play with. Quotient rule. Square the bottom, write down the bottom, diff the top, minus write down the top, diff the bottom. Be very, very careful. Don't forget your index laws. E to the x times e to the x is e to the 2x. It's not e to the x squared. So that's a classic silly mistake people make when they're not thinking, they're just working too quick. They'll go e to the x times e to the x and forget their index laws. So this one tidies up. The e to the 2x's cancel. We've got 3e to the x, e to the x plus 3 all squared. Now, well, what do we use it for? Let's find the equation of a tangent. This curve, y equals e to the 2x plus 1 at the point 1, and the exact value of y at that particular point would be e squared plus 1. So we differentiate. y dx equals 2e to the 2x. Remember, that is not the slope of the tangent. That is the formula that allows you to find the slope of the tangent. Again, the classic mistake when people are working too quick. They'll look at that and go, okay, I've differentiated, and they use 2e to the 2x as the slope. We've got to substitute in the x value, so our slope is actually 2e squared. Point slope formula, so y minus the y value, e squared plus 1, is 2e squared times x minus 1. Did I put it in general form? I did. I could have put it, I suppose, as y equals, but anyway, 2e squared x minus y minus e squared plus 1 is equal to 0. Here's one where the base is not e. Still do it the same, remember? We're just going to also multiply by the natural log of the base. So differentiate the power, 2x. The power stays the same, so we've got 4 to the power of x squared, but we also multiply by the natural log of 4 in there. I put mine in the middle. I suppose you could put it at the ends. It doesn't really matter because of multiplication, of course, you can do it in any order. Hang on. Y equals log x. Now, I put this one in because I wanted to show you why, when we differentiate a log function, all of a sudden we end up with this fraction as an answer, rather than a log function or not. So if y equals log x, let's pretend we don't know how to differentiate the log function. But I do know how to differentiate an exponential function. So I rewrite that and make x the subject, and I get x equals e to the power of y. So instead of finding dy dx, I'll find dx to y. So dx to y would be e to the power of y. Well, if that's dx to y, then dy dx is 1 over e to the power of y. But hang on, e to the power of y is x. And so there it is, 1 on x. So that's where the fraction is created. I suppose it's by turning the dy dx upside down, in this particular case, creates that fraction. We shall add those to our questions